So the next topic of discussion here is going to be the other side of instrumentation. That's going to be your probe construction. Our probe is going to be made up of various elements. You're going to have the handle. This is the part that you hold. The sheath, that's the other side that's going to hold the your temperature sensing element. The junction, which basically is how your sheath is going to be attached to your temperature sensing device, and we'll get into that here. Insulation, now there's a few different places that you're going to run into insulation. One is the insulation around your thermocouple wire, and then also we're going to talk about the insulation for your actual cable that runs from the probe to your instrument. And that's included there in cable. And then lastly, we're going to talk about different types of connectors and what connectors are used for what types of thermal temperature probe types and for their instruments. So first, the handle. Pretty common handle is ABS plastic. You can make it ergonomic. They can mold and 3D print them now. One thing to take into consideration is that they do soften at 105 degrees C, but that doesn't necessarily mean that whatever you're measuring at 105 degrees C is instantly going to melt it. You have the conduction of your sheath, and the longer that is, the longer it's going to take for whatever you're measuring to work its way up to the handle. So really, when you're dealing with ABS, if you're taking quick temperature measurements, it'll work in many applications. If you're going to be in something that's hotter than 105 degrees C for a longer period of time, you might want to look into something like a stainless steel handle for higher temperatures. A lot of times the stainless steel handles will look like a T, and there might be some type of a ceramic transition or something right there just to keep the T handle from getting hot as quickly as the thing that you're measuring. So basically the handoff there is that your stainless steel handle isn't going to melt, but it still could get fairly hot. So you need to keep that in consideration for whoever's going to be holding the probe. They probably appreciate you for that. Next, probe elements. So the sheath is the outer protective element of it. And depending on the temperature, the max temperature range that you're going to be using is going to dictate what type of material that's made out of. Now, general purpose probes are usually made out of stainless steel, and stainless steel is a relatively high max temperature of 900 C. For higher temperatures, there's this nickel alloy called Inconel 600. That'll take you up to 1150 C. And then lastly, for very high temperatures, molybdenum, I'm still working on the pronunciation of that, that'll take you up to 2400 degrees C. And that'll get you up to a high temperature, but because it has one of the highest melting points of all the pure elements, only tantalum and tungsten, as we talked about earlier, have higher melting points. It is a little rare and it is expensive, so you know, if you're getting into an application such as this, you're probably going to be looking at spending some money. Like I said though, usually most temperature measurements falling under 900 degrees C, you're going to see that stainless steel. So next we have the thermocouple junction types. And here are the three different types. Basically, just to show you here, this on the outside is going to be your sheath, which is usually going to be stainless steel. These two wires on the inside are your thermal wire, and this is a thermocouple, your thermocouple conductors. And then this is the insulation, one type of insulation, that's going to insulate your thermocouple wires from the outside sheath. Now, this first type here is ungrounded, and the reason it's called ungrounded is because your thermocouple elements are insulated from the sheath. Next is the grounded type. It's pretty much the same setup, except right here you can see that your thermocouple junction is actually bonded to the sheath. And then lastly, you have an exposed. And this is usually used for an air or gas measurement, and the obvious difference here is that there is no sheath. and you're just relying on the insulation and the thermocouple junction. This is going to have a much faster response time because you're only dealing with a small amount of mass there. So next I have a chart here giving you the advantage and disadvantages of each. For ungrounded, it's going to provide a more accurate reading because it's isolated from ground loops, but you do have a slower response because of that isolated tip. So you're going to have time for whatever you're measuring is going to have to work its way through this area here to get to your thermocouple junction, while in this configuration, as soon as it touches your sheath, it's going to start measuring your temperature. And there's the grounded, pretty much what I just said there. It's a little more intimate. The one problem you have to remember with grounded tips is that you can induce electrical noise into a circuit because you're using a thermocouple and it has that millivoltage difference. That grounded tip now can have an electrical effect on the thing that you're measuring, or vice versa. The thing that you're measuring may have an electrical effect on your instrument. Lastly, exposed, it is going to be the fastest possible, but it's for air and gas measurements only because the element's not protected. You can use it for liquid measurements, for quick measurements, but it's not really recommended. It's not going to last for a very long time. So next I want to go over thermocouple grade wire versus extension grade wire. And basically, when you have a thermocouple circuit between your instrumentation and your thermocouple probe, the entire length has to be thermocouple wire, and that means that the wire is made up of those two dissimilar metals that your thermocouple is made up of. So thermocouple grade wire is rated for accuracy over use of the full range of the thermocouple type. Extension grade wire is going to be a little less expensive, but you can use lower grade wire if you know that you're using a lower temperature gradient. So basically, let's say you're using type K and you need to measure 2,000 degrees F in type K. You're going to want to use a thermocouple grade wire because you're over on the extreme of K. Now, let's say you're using type K, but you're just measuring an oven at 300 or 400 degrees. Well, because you're not using the full span of K, you can use a cheaper extension grade wire to get to that measurement because you know you're not going outside the limits of that thermocouple span. So next we're going to talk about response time. And response time is, for anyone that's familiar with how a capacitor charges up, this is a first order system as well. And it's going to take 5 response times to reach 99% of the measurement temperature. And there's your graph there. And the response time is directly related to your thermal mass. So basically, the more mass you have in your probe, the longer the response time. And we have a demo here that we'll set up. Yeah, turn that back on. All right, I'll let that acclimate there. So let's see here. So channel 1 is going to be our blue line, and in channel 1 I have connected a immersion probe with a, this is going to be an ungrounded tip with a sheath. Now in channel 2, what I have is I have a wire probe, and that's going to be an exposed thermocouple junction. You see the insulator and there's no sheath. I'm going to give this graph just a second to normalize. There you go. All right. So what I'm going to do is I'm going to measure the temperature of this water, and we're going to watch the response rates.
It's basically sampling once a second, but you'll see just the wire probe, how much faster response is the lower mass.
Okay. And now I'm going to remove them from the element. And as you can see, our wire probe, which is channel 2, is going back to room temperature much quicker than the channel 1 probe.
I think the important learning there is that when you're using temperature probes, there's time that you have to actually wait till they normalize and get to the right point.
And notice how much quicker it was to get to a high temperature and how much longer it's taking to settle back down to a low temperature.
If you go back to the interface, we also on these we put in these indicators of the direction that the temperature is actually trending. So they go out. Let me grab this wire probe.
Go ahead.
Normalize it. They'll actually, you can see now it's warming back up, and it'll actually, when it stops incrementing, it'll flip polarity. But that's just, you know, as a practice, waiting until it's sometimes a judgment call as to when is the temperature actually achieved equilibrium on the probe, and that can often, you know, it's an operator, varies from operator to operator who spends time being careful. So it's just one minor point.
All right. Yeah, I want to hook me back up.
Yeah, so I'll get this back. I gotta do this.
Put it back to simmer. All right, so the main things to glean from that was with the less mass, we had a faster response time. And I don't know if you could tell, but I was being very careful to make sure that the immersion depth was at least 4 times the probe diameter on the one with the sheath. And that's how we were able to see that if I were moving it up and down, you would have noticed that when it reached that temperature, it would have started fluctuating. And I know this from personal experience. So it is important to get at least 4 times the probe's diameter, or it's going to start to have, it's going to see that outside air, and it's going to start to affect your measurement. All right, so here's basically an overview of different types of probe elements. As you saw, there's the wire probe, exposed junction, usually for air measurement. A lot of times, I don't know if you guys do any car work or anything like that, but if you get one of those like Craftsman voltmeters, if they throw in a temperature probe, it's going to be a wire probe like this. You know, you can push it up against things and get general temperatures, but a good rule of thumb is that if it's an exposed junction, it's mainly for gas measurement. This is an enclosed tip for an immersion probe, also helps with corrosion protection. That was the second type that I was using there. This is an immersion probe with a tapered tip, and because it has that tapered tip, there's less surface area, so you get a faster response time out of it. And this next one is for penetrating solids. This is going to be something that's used in a lot of times the food industry, checking your temperature of the chicken or whatever through the process. This next one's a little interesting. This is a surface probe to measure flat surfaces. One thing you'll notice though are these little spring looking things at the bottom. Now what that is that's actually your thermocouple junction. Technically you can call this an exposed probe, because what happens is when you take this surface probe and you push it against your surface, these spring into the probe to make good contact with the thing that you're measuring, so you can get a good measurement of that flat surface. So while you do have the sheath and you do have the ceramic, when it's all said and done, you do have an exposed thermocouple at the end. You're not going to be measuring gas or anything like that with this one, but it's great for a flat surface measurement, especially with that spring tension in there. This next one is an exposed junction, but it has kind of like a grill over it, and basically that's to just protect it from contaminants, you know, high winds, things like that. And then lastly, you have a hypodermic probe. Works very much like the tapered and the immersion, also used with food, and it's got a very fast response just because smaller surface area, faster response time. All right, next we're going to talk about wire insulation, and this is going to be the actual wire insulation of the cable coming out of the probe. So you're going to want to take this into account in your application. If, let's say, you're mounting this probe somewhere and you're mounting it in, let's say, you know, a 350-degree oven. Well, if you're putting it in a 350-degree oven, you don't want a PVC insulation because it only goes up to 221. You would want something like maybe a Kapton insulation that goes up to 500 degrees F, because, you know, the last thing you want is melting wires in your oven while you're measuring temperature. But this is just another thing to take into consideration. The insulation of your cabling, if it's going to be in the environment that you're measuring, it needs to be rated for the environment that you're measuring. All right, next is the last type of insulator I'm going to talk about, I promise. These are called ceramic thermocouple insulators. Now, there's certain instances where you run into this a lot of times in metallurgy, I apologize. When certain metals get to boiling points, they can become incredibly corrosive, much like oxygen can. And this presents a problem for stainless steel. So what the industry has come up with as a solution to this is they make these ceramic tubes, and the ceramic is going to be mixed with one of these materials depending on the maximum temperature that you're trying to measure. And the way it works is that you basically take your immersion probe, you slide it into this ceramic sheath, and then you put the whole kit and caboodle into the thing that you're measuring. And then the idea of the ceramic is that it passes through the temperature so that you can measure the temperature, but then it's protecting the material of your probe. In many cases, it's stainless steel. This way, you can get up to a higher temperature with stainless steel, and for things that start to corrode, stainless steel, which I recently found out with a customer, boiling aluminum. Stainless steel and boiling aluminum lasts maybe hours. So he was very concerned that all he could find were stainless steel probes. So what we ended up doing was hooking him up with one of these manufacturers to basically take one of our stainless steel probes, slide it into one of these, and, you know, they said it would still corrode away in about 6 months to a year, but that's still better than a few days. So I'm happy that we were able to figure that out for that customer. But you're going to run into this in higher temperature applications, and it's just good to know that this solution is available. All right, next we're going to go into the probe terminations, and this is going to be how you connect the probe to your instrument. The first type is for thermocouples. The left-hand side there is your mini TC. A lot of you guys are probably familiar with this. It replaced the standard TC connector from before, basically just for size purposes. You will still find these in industry, and many times when you're interconnecting, I've seen these used as well. Next, you have the phone plug, and this is used for resistance-based measurements, so you'll see this in RTD and thermistor applications. Next is called the TA4 uncompensated. What uncompensated means is that all of the connectors are copper. So You wouldn't want to use this with something like a thermocouple because you're introducing new dissimilar metals and new thermocouple junctions. So this is going to be best for RTD and thermistor applications. And one thing to note, as Adam was saying earlier, is that you can have a 2, 3, or 4 wire measurement RTD device. In my experience, every type of those uses this same type of connector. They just will leave out certain pins. So it's important to know what type of RTD you're using and what pins they use, and that they match up with the instrument that you're plugging into. These are all documented in spec sheets and things like that. The last connector is a little bit of a different one, as it's not it's not used in instrumentation as much as in industry, and it's an industry standard. So what we do is we try to compensate and get in there and work thermocouples in with this connector. So there's two types of M12 connectors. You have a compensated pin connector, and what compensated means is just the opposite. Instead of having a copper connector, this connector is going to have your two dissimilar metals for the thermocouple type that you're using. So if you're going to use this for a thermocouple application, you have to make sure that the M12 connector is made of the same two dissimilar metals as the thermocouple wire you're going to be connecting it to. And then the other type is uncompensated, which, as I stated before, these are going to be all copper, and since that's basically a resistance measurement, that'd be used for an RTD or thermistor application. So, pop quiz time. What features should a probe have that's going to be immersed in molten lead? And molten lead is at 621.5 degrees Fahrenheit or 327.5 degrees C. And I'll just go through and give you my recommendations here. For the handle, you're going to want a metal handle. The person using it is going to want gloves, or they also make metal handles with a ceramic transition. And as I said before, something that we didn't note here is how long is the probe going to be immersed in molten lead? And that would be something you'd want to consider in this application. For the sheath, stainless steel should work fine. As we saw, 900 degrees C was the top end for stainless steel. 327 is well within that. For the junction, ungrounded is going to be the best for molten metals, and that's because molten metals are conductive, and as we said, if you had a grounded sheath, you could introduce electrical interference and problems with that. So ungrounded is going to be the best here because you're going to be insulated from the molten metal that you're measuring. The wire grade, you're going to want to use thermocouple grade wire since you're going to such a high temperature. For insulation, and in this case I'm talking cable insulation, you're going to want something probably stainless steel. Anything that's going to be close to this or the heating elements for this molten lead, you don't want your cable melting away on you. And TC type, K should be fine. As we talked about before, K starts to drift a little bit over 500 degrees C, but since we're at 327, we should be okay with the K-style thermocouple. And lastly, the probe tip, probably for this application, the immersion would be the best type.